A butterfly flaps its wings in Brazil, and a month later, a tornado tears through Texas. You've heard this before, maybe as a joke, maybe as a mind-bending thought experiment. But here's the question almost nobody asks. Is it actually true? Where did this idea even come from? And why has one meteorologist's throwaway metaphor taken over movies, philosophy, and the way we think about our own lives? Our story starts in 1961 at MIT with a mathematician turned meteorologist named Edward Lorenz. Lorenz was trying to do something that sounds simple today: predict the weather using a computer. He'd built a basic model, 12 equations that simulated things like temperature and wind. And he'd run it over and over, generating long printouts of weather patterns. One day, he wanted to recheck a sequence from the middle of a run. Instead of starting the whole simulation over, he took a shortcut. He typed in a number from an earlier printout to restart the model partway through. The number he typed was 0.506. But the computer had actually been calculating with a more precise number internally, 0.506127. That tiny difference, 1 part in 10,000, should have been meaningless. Lorenz expected the new run to match the old one almost exactly. Instead, the two weather patterns started off looking similar. And then, within a couple of simulated months, they were completely different. Not slightly different. Unrecognizably different. Like two entirely separate weather systems. Lorenz realized he'd stumbled onto something huge. In a system like the atmosphere, an incredibly small change in the starting conditions could lead to a massively different outcome down the line. Not because the math was wrong, because that's just how the system behaved. He published his findings in 1963 in a paper called Deterministic Non-Periodic Flow. It's one of the most cited scientific papers of the 20th century. But at the time, almost nobody noticed. So where does the butterfly actually come from? In 1972, Lorenz was set to give a talk at a conference and needed a title. A colleague suggested something that would stick in people's minds forever. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Lorenz didn't claim a literal butterfly literally causes a literal tornado. That's a common misunderstanding. He was using the butterfly as a stand-in for any tiny, practically immeasurable disturbance. The point wasn't butterflies cause storms. The point was, in certain systems, we can never measure the starting conditions precisely enough to predict the outcome, because the tiniest, most trivial difference gets amplified over time into a totally different result. And there's a beautiful visual footnote here. When Lorenz plotted the behavior of his weather equations in three-dimensional space, the resulting shape looked like a pair of wings. A butterfly. It's now called the Lorenz attractor, and it's one of the most iconic images in mathematics. The universe basically drew its own logo for this idea. Let's get precise, because this idea gets watered down a lot. The butterfly effect is a property of what scientists call chaotic systems. A chaotic system isn't random. It still follows exact laws and equations. But it has one defining feature: sensitive dependence on initial conditions. That means if you start the system twice with conditions that are almost, but not exactly, identical, the two versions won't stay close together. They'll diverge, and they'll diverge fast, often exponentially. Compare that to a simple system, like a ball rolling down a smooth ramp. Nudge the start position slightly, and the ball ends up in almost the same place. Small input, small output, predictable. But weather, ocean currents, populations of animals, the stock market, the way smoke curls off a candle, these are chaotic systems. Small input, potentially enormous and unpredictable output. This is exactly why weather forecasts get less reliable the further out you go. It's not that meteorologists are bad at their jobs. It's that the atmosphere is fundamentally chaotic. Even with satellites and supercomputers, we can never measure every molecule of air perfectly, and those tiny gaps in measurement snowball. That's the real, practical reason nobody can give you an accurate forecast for a specific afternoon 3 weeks from now. It's not a technology problem. It's baked into the math. Once scientists understood chaos theory, they started spotting it everywhere. Ecology. Removing a single predator species from an environment can cascade into wildly unexpected changes in plant life, water systems, even soil composition years later. Economics. A small rumor, a single large trade, or one unexpected data release can ripple outward and shift entire markets in ways nobody predicted. Biology. The human heartbeat and brain activity show chaotic patterns, which is actually part of why cardiologists and neurologists study these signals so closely. Even orbital mechanics. The long-term position of planets in our solar system is technically chaotic. Small uncertainties today make it mathematically impossible to predict exact planetary positions tens of millions of years from now. And of course, culture ran wild with it. Movies used it as a plot device for time travel. Self-help books used it as a metaphor for how one small choice changes your whole life. It became shorthand for everything is connected, which is catchy. But it's worth being careful here. Here's where I want to slow down, because the butterfly effect gets misused constantly. It does not mean everything you do has a massive guaranteed impact on the future. It doesn't mean a butterfly is secretly steering the weather, and it doesn't mean your smallest decision today is destined to change the world. What it actually means is about predictability, not magical causation. In a chaotic system, we cannot know in advance which small changes will matter and which ones won't. Most of the butterfly's flaps do absolutely nothing. Chaos theory doesn't say small causes always produce large effects. It says we can't reliably tell which small causes will, because the system is too sensitive to trace backward or forward with any precision. That distinction matters. It's less one flap controls the weather, and more the weather is so sensitive that we can never rule out the flap. And we'll never know, after the fact, whether it mattered. So the next time someone tosses out the butterfly effect in casual conversation, you'll know the real story. An MIT scientist named Edward Lorenz, a rounding error in a 1961 computer printout, and a talk title from 1972 that turned into one of the most famous ideas in modern science. It's a genuine, mathematically real phenomenon: sensitive dependence on initial conditions in chaotic systems. It explains why we can't forecast weather 2 weeks out, why ecosystems and markets behave unpredictably, and why some of the most complex systems in the universe are, by nature, impossible to fully predict. And maybe that's the actual takeaway. Not that your every move shapes destiny, but that we live inside systems far more sensitive and interconnected than our intuition wants to admit. A little humility about what we can and can't predict. That's not a bad thing to take from a butterfly. If you enjoyed this dive into chaos theory, hit subscribe and let me know in the comments. What's a small moment in your life that you think changed everything? I'll see you in the next one.